So this is number 3 on the packet. We have a charged conductor, and it has, we're looking right here at the surface. So it also gives us the surface charge density. I'll just remind you how surface charge density is defined. It's the charge per unit area. And this presumably has a uniform surface charge density, so that's nice. So what kind of symmetry is this? This is planar symmetry, and so we're going to have like a pillbox or cylinder. So before we draw our Gaussian surface, let's just think about what the electric field looks like. If it's a conductor, then we know that the electric field is 0 inside the conductor. So what does the electric field look like outside the conductor? Well, one of the things we know about conductors is that the electric field is always perpendicular. And so, oopsies, need my pen. So it's going to look basically like that. We're going to ignore that got in there. Okay, so that's awesome. So that's kind of what our electric field looks like near the surface. So now we need to decide what our Gaussian surface is going to look like. And again, we said it was like a pillbox for cylinder, but let me just show you real quick. Okay, so here's my conductor. This is the surface, and this has words on it. So let's say this has the charge on this side, and there's nothing there. So this is the inside of the conductor. So we're going to place our Gaussian surface like this, and it's a cylinder. It has end caps with area we'll call A. And if you want to call this cylinder having a length L, that's fine. We may or may not use that. But as we're defining our Gaussian surfaces, it's always nice. Like our spherical Gaussian surfaces had radius R, that kind of thing. And so, you know, this has an area A and a length, total length L. Cool. So let's draw that in here. So this is my Gaussian surface. It's beautiful, isn't it? There's my area A on either side there. And then, if you want, this is a length L. All right, let's get going. So, Gauss's law, as always, looks like that. All right, so we've got, when we're looking at the flux, we're really trying to figure out, remember when I did the right triangular prism, when we figured out the flux through the object, we looked at the flux through each individual side, if you will. So what we can look at here is we've got this surface, right? Let's call that 1. We've got this cylindrical shell surface, let's call that 2. And then for this surface, which is on the other side here, let's call that 3. Okay, so just to do beautiful color coordination, let's talk about psi 1. So the how many lines are going through that that surface? None, because there's no electric field there, right? The electric field is 0 inside the conductor. Okay, so what about this cylindrical shell? Well, and the part that's inside the conductor has E equals 0, so that's nothing. But then when you look here, your area vectors on these sides are perpendicular to your electric field. So it's just grazing it. And so that's also going to be 0. So the only thing that's going to give you a flux is this third guy, okay? So phi 3 is E times that area, right? That area of that. Okay, cool. So that's phi 3. So that means that the total, right, the net flux is just EA. So that's the left side of Gauss's law, all right? So we have EA equals Planck over epsilon naught. Okay, so let's go to the next page with that. So here we are. We have an area right here that contains a certain amount of charge, right? And we want to know how much charge is enclosed in that area, okay? So what do we know? We know that sigma is Q over A, right? And we want to know the amount of charge. And so that is just sigma times A. And we are given sigma, right? So let's plug that in. So our left-hand side's EA. Our Planck is sigma times A. So guess what? The area of our Gaussian surface, those little end caps, did not matter. And we get this very important result, which is that the electric field near the surface of a charge conductor. This will be used over and over and over. So that's the value is sigma over epsilon naught, and of course it is perpendicular to it. If it was a negatively charged conductor, then it would be that way. Okay.